Welcome everyone to this week's tutorial, which is all about multiple linear regression analyses and is in some ways the final piece of the puzzle for your lab report, because this is the final component of knowing how to apply the knowledge that we've learned in multiple linear regressions to your lab report to be able to work through that section. And so really, today we're going to be focusing on talking about the general steps for multiple linear regression analyses, conducting the analyses, and some sample write-ups. So that's really the focus of today, and it'll all translate onto the skills you need for your lab report. So the steps for multiple linear regression analyses, this is all from the lecture, but they include drawing your model, identifying your independent and dependent variable. And as I mentioned in the lecture, this is something I still do to this day. I identify what is my independent variable or independent variables, what is my dependent variable, and what are their relations to one another, in addition to other variables that are unmeasured that may also have an impact. And that's important in thinking about your question of interest, identifying what the relationships may be and what may influence it and what you need to control for. So drawing your model is important, and we'll talk about that more in a second. Checking the assumptions, choosing the type of multiple linear regression and running it, interpreting the output, and if meaningful, writing the regression equation. So in terms of each of these steps, so what I was talking about before related to the path diagrams, that's what I do, where I look at the arrows and where they may relate. And this can be really detailed. You can get to the level of actually writing what the average effect you may suspect would be for each of the relationships between variables. But at this stage, at this level, when you're thinking of path diagrams, what I want you to be thinking about at a minimum is, firstly, with your diagram, what are all the variables that should be included based on your reading of the literature, and then starting to think about what are the direction of the effects. Is it positive? Is it negative? Is there mixed evidence? And then if you are building your capacity in critical thinking and understanding, then that's when you want to start thinking about, well, what are the size of the effects and which ones have the largest magnitude of effects? That's sort of the order of progressing. You can also create a Venn diagram, but this is really hard with more predictors, as you've seen from the lectures, and it's largely a teaching tool to help explain how you have the variance shared between an independent variable and a dependent variable. And then you have, when you have multiple independent variables, you have, sorry, I'm just, if for those online now, you can just see the camera and I'm just like blocking my face with hand signals. But what I'm trying to convey through my hands is that the shared variance and unique variance. If you want a more of a detailed summary of that, that's all in the lectures. But really, that's the Venn diagram and what that is useful for conceptualizing. But then you can progress to the assumptions of multiple linear regression analyses. And by the end of today, if you don't already have a good understanding of these assumptions and what the tests are that relate to them, you certainly will by the end of this tutorial, because we'll be hammering these assumptions in every time we run the regression analyses. So these include level of measurement. Is it interval? Is it ratio? Or is it categorical, which is acceptable in a regression analysis, as we saw in the lecture? The sample size requirements, normality of variables, linearity, homoscedasticity, multicollinearity, and residuals are normally distributed. So these are the assumptions, and we'll go through them in more detail as we progress through the examples. And we talk about the types of linear regression, and these include standard, where you just have all the independent variables and dependent variable in your model at once. Hierarchical, where you have multiple levels of the model, and you're asking, even though the model from a standard and hierarchical may be the same, they may overlap, they're asking slightly different questions. Standard is saying, what is the relationship between this independent variable and the dependent variable after controlling for all other covariates? Hierarchical is asking the question of, does this variable or set of variables explain additional variance over and above this initial set or individual variable? And that's hierarchical regression model. Stepwise forward and backward is used a lot for when you're using statistics or computational models to derive the methodology. But for this course, we're focusing on standard and hierarchical. And in this tutorial, I'll show you how to do both in Jamovi. So that's the focus of today. So in saying that, let's open up this. We'll do our standard multiple linear regression using the first data set. So if you navigate to week 8, scroll down and select data set 1, you can load that up in Jamovi. And this data set focuses on deterrence theory. Whether or not one obeys the law depends on how likely they think punishment for disobeying is. Am I sharing my screen? I am not sharing my screen. Let me, no, I do not. I do not. That is, let me share my screen. Share application screen. Select entire screen. Boom. Okay. All right, we're on. Can you see this? You can see this. Jamovi. Okay, here is the slides. I was working through the slides. Great. Sorry. Hey guys, it's not like we're only 4 tutorials in, you know, eight hours deep into tutorials. It's you know, I need a bit more practice to really hone in on my skills. We were just talking before the tutorial started about production quality, so this is something to keep in mind. So all the slides are there. These are what I was talking through, really the overview of the background for today's tutorial. So the standard multiple linear regression is, here we're going to be looking at the example of deterrence theory. So whether or not one obeys the law depends on how likely they think punishment for disobeying is. And so the question we're asking is, do certainty and severity predict compliance? So here's certainty of getting caught and severity of consequences. And our dependent variable here is compliance with the law. So what I want you to do is pull up the data set. So you go import your data. Tutorial 4, data 1. Open, and I'll delete these. Okay, so here's our variables. We have compliance with the law, certainty of getting caught, severity of consequences, and we'll talk about legitimacy in a moment. What do you observe in this data set first off? How many observations do we have? $62, excellent. Well, how did you work that out? Row count, excellent. So down here you have row count, so 62 observations. Very, very good. So that is how many observations. How many variables do we have? 4, excellent, Tatiana. So we have 4 variables, which are compliance, certainty, severity, legitimacy. ID is not really a variable, it's just an identifier, yeah? So that's important when we consider our cases to variable ratio. So this depends on the analyses that we are doing. So that is this one. So the first analysis is two independent variables and a dependent variable. So we're just using these 3 variables in total. And so to evaluate sample size, enough data is needed to provide reliable estimates of the correlations between variables. So if n is greater than 50 cases plus n greater than 10 to 20 cases times the number of independent variables, then that's deemed as a sufficient metric. Otherwise, the estimates of the regression line are probably unstable and are unlikely to replicate if the study is repeated. In our case, we have 4 variables, but in our model we have 2 independent variables. And so for this threshold, n is greater than 50 plus, let's say, take the lower part of this threshold, 10 times 2 independent variables, because we have 2 independent variables here. So 10 times 2 is 20. Well, it's n greater than 10. So it should be 11 times 2 is 22, plus, say, 51 gives us 73. So do our data meet the requirements for this threshold? Yep, let me have a check. So the data, say we have row count of 62. So 62, and this is saying with this formula, that we need 73. So it actually wouldn't meet the requirements for our analyses. So it doesn't meet the assumption there, but there are many different, that's right, there are many different types of criteria that you can use or reference. Here's another one, 50 plus 8 times k, and k is the number of independent variables. So In here, it's 2 times 8 is 16, plus 50 is 66. Does our data meet that criteria? Nope, yeah, thumbs down is appropriate. So 0 for 2. 104 plus K, we definitely know it's not meeting that because it's less than 104. And this is all based on detecting a medium effect size with a critical alpha less than 0.05 and power of 80%. So overall, there's another one that says have 10 to 20 times as many observations as independent variables. Using that threshold, if we have, say, 2 independent variables and we have 62 observations, then that would meet the criteria there. So we could reference this criteria and say it meets the threshold. But overall, I think you can see that it's not meeting many of the criteria and it's meeting one. And so that gives an indication that ideally, if we were able to collect more data and conduct the study, we would, but we can't, and so this is what we're left with, and this is the criteria. What would we do if all of the criteria were not met? If all the criteria were not met and you can't collect more data, which is the ideal situation, then you can proceed with your analysis, but just acknowledge that you are less likely to have stable estimates for your analyses. And we'll touch on this towards the end about troubleshooting, about what to do when you don't have enough data or some other situations that commonly arise. So let's get started with some analyses. We'll go through to check descriptive statistics. So go to analyses, exploration, descriptives should be second nature to you now. Add in the variables of interest, so compliance, certainty, and severity. And we'll get some skewness and kurtosis statistics and some beautiful plots going. So hopefully everyone's got that loaded up now. So what we can see is there's 62 observations, no missing data, and we can see these distributions that are here. How do these distributions look? What do you think? Normal, fairly normal. Yeah, I agree with all of you. They're pretty normal distributions. They look pretty nice, and there's no issues with the skewness or kurtosis statistics there. They're within threshold. So all of this looks really, really good. So the next thing that we'll be doing after that and plotting histograms is running a correlation matrix to see if there are any relationships between our variables. It also allows us to test for multicollinearity, but we also have another test for multicollinearity called the variance inflation factor. All this is covered in the lecture, but I'm just reiterating here for clarity. So we're asking the question, are our variables related? So let's we go to regression correlation matrix. And we put in our variables of interest, and we have our correlation matrix here. And so we're asking the question, are our variables related? Are there linear relations between independent variables and dependent variables? So for the first questions, are our variables related? What do you think? Looking here. Any ideas? Are there relationships between variables? This is back to week 3, week 4 correlations. What do we think? Yes, no, unsure? Are we leaving legitimacy out of our correlation matrix? Sorry, Connor, yeah, we are, because the question we're answering is this one for now. Do certainty and severity predict compliance? So compliance with the law is our dependent variable, certainty and severity is our independent variable. So for now, we're just looking at these 3 variables. Yeah. And yeah, we'll leave it out of the descriptives for now too as well. Yeah, excellent. So looking at this correlation matrix, what do we see in terms of are our variables related? What can you say? Yes, no, unsure? Yeah, no worries. That's all good. So we'll start by looking at Pearson's R, which is the correlation. So we see a 0.119 correlation between certainty and compliance, a 0.083 correlation between severity and compliance, and a 0.333 correlation between severity and certainty. And then when we look at the p-values, we see it's greater than 0.05 for certainty and compliance, so it's not significant. Greater than 0.05 for severity and compliance, so not significant. And it's less than 0.05 for severity and certainty, so it's significant there. So we see a significant positive correlation between severity and certainty. The other two are non-significant. Right? So that's the key takeaway there. The next question is, are there linear relations between independent variables and dependent variables? Does anyone remember from the lecture how we assess this? Whether there are linear relations between these variables? The plot, yes, spot on, Luella. We do a plot. So tick correlation matrix plot. And we have our plot, remembering that it'll always fit a straight line. So we're not looking at whether the line is straight. We're looking at the data points. And we're trying to see, is there any indication of nonlinearity that's here? So like a curve in the data points that's occurring. And here, there's some gaps, likely due to a lack of data or missing data or restriction of ranges in certain areas, but there's no missing, there's no nonlinearity. There's no evidence for saying that it's nonlinear compared to linear. So I would say you're okay to say that there's a linear relationship between the variables here. And now let's have a go at doing our first regression. So to do a regression, what we do is we go into regression and we select linear regression, and we'll put compliance in the dependent variable list and severity and certainty in the covariates list. And we want to select a few things. Go into assumption checks. We want to check the assumption of normality through the QQ plot, fitted versus residuals, multivariate outliers through Cook's distance, multicollinearity through variance inflation factors. We want to look at whether our model has a good fit to our sample through R squared and through the population through adjusted R squared. Overall model test with F test, and model coefficient, we want standardized estimate and confidence intervals. These are all covered in the lecture as the assumptions that we are looking to test for when we're running multiple linear regression analyses. Okay, so I'll give you a moment. I'll keep it on these ticks, and you can make sure that your output looks the same as mine. Everyone okay? Yeah, excellent. Thanks, Luella. So let's work through this step by step. Let's start with some of the assumptions, right? First, let's look at this QQ plot. Does anyone remember what the QQ plot is assessing? What assumption it's assessing? Sorry, there's going to be a lot of questions today, by the way, and it's going to be hard for the first example, but once we drill down and you get a sense of the connections, it'll be easier as the examples go on. But for the QQ plot, what assumption is it assessing? Normality, excellent, Noella. Yeah, it's the assumption of normality of the residuals, and that is why we have these standardized residuals on the y-axis. And does anyone remember what we're trying to look for in this plot? What do we want it to look like? Perfect, Rochelle. You want the dots to cluster along the line in the middle. It's okay if along the edges it deviates, which is okay, but generally you want the dots to align to the middle. So what we see there is that the dots do align to the middle there, right? So that is a good indication that our residuals are normally distributed. Right? So that's the key takeaway there. Then we have the fitted versus residuals plot. Does anyone know what assumption this is assessing? The key assumption it's assessing? It's a long word. Hard to type probably as well, or spell. Any ideas? It's okay if you don't. Something skedasticity. Yeah, you're all over it, Every. That's it. Homoskedasticity or heteroskedasticity. So we want our data to be homoskedastic, which is where the data looks like this, and it's like a diffuse cloud of points. But if it's heteroskedastic, or if there's some funneling occurring, that's where we may have a problem with our data. So I'll show you some examples later on as to what heteroskedastic data looks like. Great. So that's our assumptions for that. What about Cook's distance? Does anyone remember what assumption that's assessing? So Cook's distance is assessing multivariate outliers, distance of the residuals. Yeah, in some ways, which variables were dependent covariate factors weights? Connor says, okay, yeah, let's the dependent variable is the compliance, and independent variables is certainty and severity. No need for factors or weights at this stage. We're just running it. Then this is all you need for running a regression. Yeah. Thanks for letting me know. So in terms of Cook's distance, it's multivariate outliers, and you want to see if there are any values greater than 1 that would indicate that you have a multivariate outlier. But here it's the maximum value is 0.1. So that gives us a good confidence that there's no multivariate outliers in our data set. And the key thing that, well, what usually happens with Cook's distance in software is it plots it for, maps it out for every single participant. For some reason, Jamovi doesn't seem to trust you with that data, so they just give you the summary statistics. But ideally, it gives it to you for every participant. And then if you find that the maximum value is greater than 1, then you would identify those participants, remove them, run the analyses with them, run the analyses without them, and see if the results change. Here, you can't do that. You can just check whether there is an influential outlier or not. You could maybe guess which one, but that's very difficult to do. And so ultimately, it's just a yes or no, is it meeting the assumption? And then we have the collinearity, which is the variance inflation factor and tolerance. We want variance inflation factor to be less than 3, tolerance to be greater than 0.3. And what this relates to, and they're both the same thing, they're just the inverse of one another. And what that relates to is whether your variables are highly correlated with one another. And so if they are highly correlated, they're essentially measuring the same thing, and this can give you unstable estimates in addition to challenges with the amount of variance they account for in your dependent variables. So here we see the variance inflation factor is less than 3. So this indicates that there's no multicollinearity in our data set, and we sort of had a sense of that from our correlation table here, matrix here. Yeah, so that is pretty much every assumption. And so these residuals and plots you can ignore because they're actually the variables mapped against the residuals. The key one you need is that first one, fitted versus residuals. The QQ plot for normality of your residuals, your collinearity statistics, your Cook's distance for multivariate outliers, and that's it for assumptions. Does that make sense? Any questions about that? No, all good? It's a dangerous topic to take silence as agreeing. So I'm gonna wait for a response. Thanks, Lola. All good to hear. And let me know if there's things you don't understand. We'll do lots of examples as well, so that'll help. So now we have the model fit measures and the exciting model coefficients. So we get a sense as to the relationship between our variables. But before we get to the exciting bit, I mean, it's all exciting, but before we get to that, we have to talk first about the model fit measures. What do the model fit measures do? Well, this overall model test is an ANOVA that compares our model to the mean of the dependent variable, here the mean of compliance. So it has our data, and it fits the mean through that data and says, does this fit the data better than our model? Or does our model fit the data better than the mean, rather? And what we find is the p-value is 0.3, so it's greater than 0.05. So in fact, what this is saying is our model is useless. It doesn't predict the variance in the data any better than using just the mean of compliance. If I took the average compliance, that would fit would be a line that fits the data points better than using this this model, this fancy model. And so at this point, you question life choices with the whole meaning of what's going on with the theory, and fundamentally you stop there. You don't really interpret these estimates because they're meaningless, right? They don't mean anything because the model is saying that it's essentially a meaningless model. But let's continue for the sake of teaching as to what this, how we would interpret the rest of the model. So we have capital R, R squared, adjusted R squared. Do people know what these mean? Have a go at any of them. Capital R, R squared, just R. Shared variance, that's right. Luella, do you know which one is a shared variance? When you R squared, you get the percentage. Yeah, spot on, Rochelle. Yeah. So we have little r, which was used when you have two variables. Yeah, you're right, Luella. So you have little r when you have two variables, and it's looking at the correlation between the two, like we see here, Pearson's R, right? Little r. Capital R is the correlation between variables accounting for covariance. So it's used in regression models. R squared is the amount of variance in the dependent variable accounted for by our model. So here we have 3.9%, almost 4% of the variance accounted for. That's in our sample. Adjusted R squared is in relation to the population. So this is at the population level. We have 0.7% of variance is accounted for by our model. And this makes sense given that our model is meaningless, right? Now, why is adjusted R squared less than R squared? It's sort of, the key thing is if you look at the formulas for these two measures, you'll see that adjusted R squared, in fact, is weighted and accounts for the number of predictors. So if I was to just put in 10 nonsense predictors into this model, R squared actually inflates arbitrarily. It actually increases with the number of predictors. So it's important to keep an eye on adjusted R squared and to see what that means, because it accounts for the number of predictors. So it should always be smaller than R squared. It also relates to the population level, whereas R squared is about the sample level. And then we have our estimates, right? So this estimate is telling us a few things. First, for every 1 unit increase in certainty, there's a 0.15 increase in compliance, yeah? So as certainty increases, compliance increases. Specifically, every 1 unit increase in certainty, there's this much increase in compliance. So that's how you read these numbers in the estimate. Again, here, for every 1 unit increase in severity, there's a 0.015 increase in compliance. So that's the key takeaways there. Both of these are non-significant. Again, our model is not significant, but we're just going through the process of interpreting these measures. The standard estimate tells us the magnitude of effects relative to one another, so it's in standardized units. And this is saying that certainty is larger than severity. So certainty is larger than severity. And we can use the confidence intervals to get a sense as to if this is significantly larger. So if the confidence intervals don't overlap, so here's negative 0.07 to 0.46, and this is negative 0.25 to 0.29. So they do overlap, the numbers overlap between the two. And so as a result, there's no significant difference between the size of effects, and largely the relationships are no different to 0. So it's despite the direction we see, the p-value is greater than 0.05. So it's no different than 0. So that is the key takeaway. So that's how you sort of interpret the model fit measures, and then the coefficient measures as well. Let me make sure I've hit everything here. Some additional questions. So we've interpreted the model fit measures. For the regression coefficients, if certainty and severity are 0, what is the rate of compliance? Does anyone know? If we were to set certainty and severity to 0, what would be the rate of compliance? It all comes down to the regression formula. So y equals intercept plus independent variable 1 plus independent variable 2. So if the value of certainty and severity was 0, like if the values were 0, what would the dependent variable or compliance be? And it all comes down to that formula, because when you set the independent variables to 0, or when the x-axis is set to 0, then y is equal to wherever the intercept is. And so that's what this value represents. So the intercept, 2.96, is when x is equal to 0, then that's what the intercept. It's not necessarily x equals 0 because it's not two-dimensional, it's three-dimensional or more because we have multiple variables. But you can think of it as if you say we did just have the two variables, right? This is the relationship between certainty and compliance, right, which is 0.16. And if certainty was 0, if we had zero certainty, if we had zero certainty, then compliance would by nature be 3.024. And if you add in severity, you could then say the same thing. If severity and certainty are 0, the intercept is 2.96. So in some cases, the intercept is meaningless. It doesn't make sense to set something to 0. But in other cases, you can see it's more meaningful. So if everything was set to 0, where does it intersect the y-axis? And so we'll come back to that as we progress through the examples. Which values go into the regression equation? That is the estimates. So this is our intercept estimate. Here's our beta slope for the certainty value and our beta slope for the severity value. And Cook's distance we looked at, QQ plot, and fitted and residual. So we're happy with all of our assumptions. So what did we find? What type of regression did we do? We did a simple or simultaneous linear regression. What were our assumptions? Were we okay on sample size? You could argue, yes, we met criteria for one, but arguably, I think there's just a equal rationale for saying no. Linearity, multicollinearity, and distribution of residuals were met. Were there any multivariate outliers? Cook's distance says no. And findings, how well did our independent variables predict or explain the dependent variable? Not well at all. Our model was awful. Yeah. And so the write-up should include these components, which will may seem overwhelming at this stage, but will become second nature the more and more you interpret multiple linear regression analyses in terms of the model output. So R squared, and adjusted R squared. If it's hierarchical, you're looking at the change in R squared, and then your inferential tests like the ANOVAs that was done for the model. Significance, size, direction, and relative contribution of each variable. So significance is determined by the p-value. Direction is determined by the estimates, like they're all positive here. And the size of the effect is determined by the standardized estimate. So that's the key things there. And statistical significance, TP, yeah, that's everything. And so you can have a table that includes all of these key components: correlations, beta for intercept and independent variables, beta value, standardized beta, statistical significance, T and P value, and the direction and size of the results. And you want to consider the percentage of explained variance through R squared. So that is all of the key points that you want to be including in the write-up. And so here is an example write-up. So you can say we were interested in the extent to which severity and certainty of punishment predicts increased compliance with the law, or you could, if stating it in third person is the purpose of this study was to investigate the extent to which severity and certainty of punishment predicts increased compliance with the law. In the zero order correlations presented in table 1, where's my table 1? Oh, it's a fictitious table 1, sorry. The two predictors are moderately correlated with each other without violating the assumption of multicollinearity, though not significantly related to compliance. So that's just describing what we see here in our correlation table. Yeah. The compliance with the law was regressed onto severity and certainty using simultaneous or standard multiple linear regression. This analysis was appropriate, as you could argue we had sufficient sample size, or maybe you could say that we had sufficient sample size and specify the criteria, but not for the other criteria. Variables were related in a linear fashion based on examination of scatter plots. Cook's distance did not suggest the presence of multivariate outliers, and the QQ plot indicates residuals are approximately normally distributed. The predictors explain 4% of the variance in the dependent variable, and that's what we see here. So 4% of the variance in the dependent variable is explained by the predictors. And the overall model was not significant. Neither certainty nor severity were significant predictors, indicating that any apparent relationship these have with compliance could be due to chance, right? So that's an example write-up. There's certainly ways to improve it by using third person in addition to, I think you could, this sample size could be a bit more transparent in stating that the sample size did not meet certain criteria, but it did meet some, and interpreting what that means in the sense of the reliability of the estimates, and it may produce unstable estimates. But in any case, these are the key components of your analyses. Excellent. So that is everything there. What we'll do now is a hierarchical multiple linear regression. So we have our same data set. We're going to expand the deterrence theory model to include an additional predictor, which is perceived legitimacy of the authority. Can adding legitimacy explain additional variance over and above certainty and severity? So this is our first model, which we just ran. And now we're saying, can adding legitimacy of authority explain additional variance over and above our initial two variables? So to do this, well, first we need to look at sample size. We have 62 and now we have 3 predictors. Is it enough? Not really, although it was arguably not enough in the first case. The sample size could give us trustworthy estimates of the overall regression, R and R squared values, but we might not get reliable estimates for the individual predictors, so the betas and the standardized betas. So we have to just acknowledge this if we move ahead, which we will. Linearity and multicollinearity, we need to check correlations and request a correlation matrix plot to examine the correlation. So you can either, we'll run it again rather than loading it up. So we'll go regression, correlation matrix, and this time we're popping everything across. Okay, and the plots. Let's start with the correlation matrix. What do you see here? Any thoughts? How would you interpret this correlation matrix? Any ideas? What are we thinking? So we have a correlation matrix. P-value for legitimacy is significant for compliance and certainty. Let's have a look. So P-value for legitimacy is significant for compliance and certainty. Yeah, that's right. So there's a significant positive correlation between legitimacy and compliance, and certainty and legitimacy. Excellent. Anything else we see? Rochelle says severity and certainty are significant. Yeah, there's a positive correlation between severity and certainty. Remember, this first half of the correlation plot is exactly the same as the correlation plot. Oh, is it gone? No, here, yeah? So severity, certainty, 0.33, 0.008 is the p-value, and here is the same. It's the same sort of correlation matrix, but now we have legitimacy here as another variable. And when we look at the plots, we can see that the data is linear. There's linear distributions of the data or no clear nonlinear distributions. So that's good. And so, yeah, we've examined the scatter plot through here. So the next step is to start running our analyses. So all of these assumptions are the same when we have our analyses. To get back to your analyses, by the way, just double click this plot and it goes back to your analyses, or you can work through each of the steps again. And this time we're adding legitimacy. So how do we get a hierarchical model? We go through to Model Builder, Add New Block. So that was Model Builder, Add New Block, and then you put legitimacy across as a covariate. And for me, it automatically put it across into the new block, but if it didn't for you, and it's still over here, you just select your block, select the variable, and use the arrow to bring it across. Yeah. And if you say move one of severity across and you want to put it back, you select that block, select the variable, move the arrow, and it'll bring it across. Yeah. So this will create a hierarchical model, and it'll show you by default Model 2, or I think it should on your end, which has all the variables. And if you flick to Model 1, that's the model we ran prior. Legitimacy isn't there for you. Is it not there? Maybe it's still in your column here. So you need to pull it across into your covariates. So get legitimacy, pull it into covariates, and then, yeah, no worries, Lola, awesome. And then select your block 2, or add new block if you haven't done that, and then pull legitimacy into there. Yeah. So now, excellent. So now you've run your hierarchical regression model. Keeping in mind, Model 1 is exactly the same as what we ran before. Model 2 is the difference. And this question is asking, what the question is asking is, does legitimacy explain variance over and above the variance of our certainty and severity? Yeah. And so we have our model fit measures. Again, what does our overall model test look at? What is it assessing? How useful the model is yet in a nutshell, but it's comparing something specifically for each of these models. What is it comparing? Anyone remember? Not quite, Emery. So that is looking at our model comparison over here. So these model fit measures are looking at, for each of these models, do they fit the data better than the mean of your dependent variable? So here is the mean of compliance. So for the first model, which we did, which just had certainty and severity in it, the model didn't fit the data any better than the mean. So the mean was actually just as good as that model. In the second model, which added legitimacy in as an independent variable, it is significantly better than the mean of compliance. So this says our model with legitimacy included into it explains the variance better than the mean of compliance, which is what you're after as a very baseline test. Yeah. So this is indicating to us that it's good, and so we can start interpreting what the coefficients refer to. We have here our R squared. So what's the amount of variance in compliance accounted for in model 2? Point 26052. No, that's, yeah, I mean, technically you're right. That's 052, but that's the adjusted R squared for the population. So that's the amount of variance accounted for in the population for compliance. But this is in our sample, it's 0.29. So it depends if you're reporting adjusted or R squared. One's for the population, this one's for the sample, saying 29.69% of variance in our sample is accounted for. Yeah, excellent. And then we have delta R squared, which compares model 2 to model 1 and subtracts the two. So 29.69 minus 3.99 gives you 25.7%. So this says, by adding legitimacy into our model, we explain an additional, or account for an additional 25.7% of variance in compliance. Yeah? By adding legitimacy into our model, by adding that additional variable, we can explain an additional 25.7% of the variance in compliance. That's really, really good. And then we have of course, our Cook's distance and variance inflation factor. They're all looking good, and so is our fitted versus residuals. So all of our assumptions are met. So now we can start interpreting our table of coefficients. Can someone try to interpret something in this table? So pull out something and try to interpret it for me. So it could be the estimates, the p-values, standard estimates, confidence intervals. What is it? What does it say? What does it mean? Let me know if you're unsure about anything as well. If not, just have a go. Emery says legitimacy is significant for compliance. Excellent. So Emery is looking at the p-values and sees that legitimacy is significant for compliance, which is legitimacy is significant, significantly related to compliance after accounting for severity and certainty. So there's a less than 0.05 p-value. Rochelle says the legitimacy estimates do not overlap. So legitimacy and the p-value is significant. So legitimacy estimates do not overlap. So I'm assuming, Rochelle, you're looking at this 0.312 and the 0.792, and you're seeing that it does not overlap with the negative 0.246 and 0.223, and the negative 0.265 and 0.236. So this confidence interval is quite far ahead of these two. And so that would mean we could say legitimacy is the largest predictor of compliance through the standardized estimates. And it's because it's doesn't overlap, as Rochelle said, then we can say that it's significantly larger than severity and significantly larger than certainty in its prediction or as a effect size. So that is those are the key things there. We've interpreted the p-values, excellent. So we've done these 4 columns. I guess I don't really understand why squaring R makes it smaller. When I think of squaring, I think of multiplying a number by itself, but I suppose it's not normal squaring math function. Yeah, it is the normal squaring math function. So you are multiplying it by itself. So I'm not sure well what that relates to, but feel free to let me know. But yeah, usually when you look at R squared, so say in a simple linear regression model, so let me pull it out. So in this simple linear regression model, R like Pearson's R is just the correlation between certainty and compliance. And then if you square it, you'll get R squared. So if I pull into terminal and let's say 0.16. So if I get 0.16 and I square it, yeah, you get 0.0256. That does not map on here. Why does that not map on here? Oh, is it because it's something to do with the hierarchical? No. 0.1. Oh, interesting. When you just put the variables in, so certainty and compliance, it's so, oh, because it's this is the estimate rather. Sorry. So we work backwards here. So let me get the R squared for certainty and compliance is 0.396. Yeah. So the square root of that R squared, yeah, gives you 0.198, which should be certainty and compliance. That's the correlation, Pearson's correlation here. So here it says 0.199. So when you square that correlation, 0.199, that gives you the R squared. But these estimates are not the Pearson's R. This is saying for every 1 unit increase in certainty, there's a 0.16 increase in compliance. So it's actually interpreting that linear slope. Yeah, excellent, Willa. Good to hear that helped. No worries. So what were we up to? We were interpreting everything. So let me bring this all across. Oh yeah, we were interpreting, the last bit was the estimates. So I mean, I guess I've sort of done that through that example, but the interpretation here for these estimates are, for every 1 unit increase in legitimacy, there's a 0.54563 increase in compliance, yeah? And again, similarly, for every 1 unit increase in severity, there's a 0.008 decrease in compliance, but that's non-significant. So it's no different to 0, and similarly for certainty, it's there. So this says, as legitimacy increases, so does compliance. And if you want to be precise about it, it's every 0.54 increase in legitimacy is every 1 unit increase in legitimacy is a 0.54 increase in compliance. That's probably the biggest thing that people wrap their heads around when reading this table, is thinking that it's about legitimacy, this number, but actually this relates to changes in compliance with a 1 unit increase in your independent variables. That's if you keep with that structure of it, for every 1 unit increase in compliance, we see a X amount increase in legitimacy, then you'll always be able to interpret these sort of estimates. For the standardized estimates, you take it as standard deviation. So for every 1 standard deviation increase in legitimacy, there's a 0.5523 increase in compliance. Yeah. So that's the main takeaways there. Great. So that is our model. We have run it, and you can toggle between your models as I've shown you. You can flick back and forth, and you get the 2 models there, which is a nice feature. So the main things, what did we do and what did we find? What type of regression? We did a hierarchical regression. Were we okay on sample size? No, but we were for linearity, multicollinearity, and distribution of residuals. Were there any multivariate outliers? No, Cook's distance was less than 1. And how well did our independent variables predict or explain our dependent variable? Well, yes, our legitimacy was related to compliance after adjusting for, let me put back to the Jamovi. Legitimacy was associated with compliance after adjusting for severity and certainty. That after adjusting bit is really, really important, because these estimates will change. You see how it says 0.54? If I flick these variables out, oh, it still says 0.54. Oh, I know, now it gives you nothing. But often at times these estimates can change when now it's giving me nothing. Oh. I don't know why that's the case, but these, oh, because it's dragged it all into block 2. Okay, okay. So let me pull this across and then pop it into block 1. Okay, so these estimates can change, yeah, thank you, Ula, depending on what variables are included in the model. So every time you interpret the estimate, this is the relationship between X and Y after controlling for these other independent variables. And that's really, really important because these estimates change as a function of the other variables that are there, and the interpretation is specific to what it means when you're controlling for other variables. So that when you're reading papers and you see one paper shows an effect, the other doesn't, that's where you're looking at the regression models to see, well, do they control for the same variables? Perhaps one controls for additional variables that the other did not control for, and that could explain the difference between the findings between the two papers. And so this is an important interpretation or nuance when we're considering our interpretation there. Excellent. So the example write-up is we tested the prediction that perceived legitimacy of the law would explain variance in compliance above and beyond certainty and severity of punishment using hierarchical multiple linear regression. But we're going to start by talking about the correlation matrix. So based on correlations between variables, legitimacy was strongly positively correlated with compliance, and that's the Pearson's correlation there with the p-value, indicating that more legitimate individuals perceive the law, the more they tend to comply. While legitimacy was also significantly correlated with certainty, this association was weak with 0.39, and there was no significant relationship with severity with p-value greater than 0.05. Therefore, we were not concerned about potential multicollinearity, but again, we can assess that using variance inflation factor and the tolerance statistics, or this as well. But typically variance inflation factor. Examinations of the scatter plots indicated that all relationships between variables were linear. Compliance with the law was regressed onto severity and certainty in step 1 and legitimacy in step 2. So now we're going to talk about the multiple linear regression analyses. The results confirmed there were no issues with multivariate outliers, with Cook's distance less than 1 or 0.17, the maximum one, and residuals approximated normal based on the QQ plot. The first step of the model did not fit the data well, as we explained in the previous example, and explained a non-significant small portion of the variance in compliance, which is 4%. Adding legitimacy as a predictor in step 2 explained an additional 26% of the variance, which is what we saw with our delta R squared. 26% of the variance was accounted for, and that's what I've reported here. Legitimacy was a significant positive predictor of compliance based on non-overlapping confidence intervals, as Rochelle said. Legitimacy was the significantly strongest predictor, and the association is interpreted to mean that the greater perceived legitimacy predicts an increase in compliance. However, and we're coming back to the sample size assumption not being met, as the sample size for this analysis was low, the estimates for each predictor are potentially unreliable. So that puts everything we discussed and worked through, from the correlation table to the multiple linear regression analyses to the standardized estimates and the confidence intervals, into written form. So hopefully that helps understanding what's there. And here is an example of this in a table form that's APA formatted. So you have step 1, where you have the unstandardized and standardized betas, t-values and p-values. And step 2, you have the same with legitimacy in there as well. Yeah? And you can see how these estimates change as a function of including legitimacy into the model. Yeah? Excellent. Any questions about any of that? No? In saying that, I think you all deserve 10-minute break. What does T stand for again? No, that's fair. So the T is the T statistic. So let's go back to, you'll still get a 10-minute break, don't worry. Okay, but the T value is the T statistic. How it's calculated is actually, you get the estimate and you divide it by the standard error and it gives you the T value. So for legitimacy, if you don't believe me, you get 0.54563 and you divide it by 0.1185, we should get 4.6039. So that's the T, that's how you calculate the T statistic. And then using the T distribution, you can get the P value. And that's all the T relates to. So this is just the estimate over the standard error would give you the T value, which you can use to calculate the P value. And so whether the result is statistically significant or not. Excellent. Great. In saying that, enjoy a 10-minute break or yeah, I will take a minute off because we have a lot to do. So I'll give you 9.5 minutes. I feel there's a fair compromise. We'll regroup in 9.5 minutes, and then we'll get on with the rest of the tutorial. So grab a tea, stretch your legs, reflect on what we've learned, and we'll come back. You can listen to the rain outside your window. That's storming. I'm running home after a meeting I have after this tutorial. So that will be interesting. So big warm thoughts. Okay, have a break. See you in a minute. Hey guys, how we going? Let's get stuck back into it. Hopefully you are refreshed, ready to go. I have popped the light back on, and for some reason the video is very grainy, but that is what happens when it is pitch black outside, but light on the inside with all the lights. Hi, hello, everyone's back. Good to hear. Um, let's get stuck into example 3. So let's download tutorial. We'll go into new here. Get rid of that. Let's download the new tutorial data set. So you can go into week 8, download that data. I'll go into special import, browse, tutorial 4, data set 2. Excellent. So you've got your data set loaded, or have a load of it once it's ready. And this data set relates to English achievement. So the research question is, to what extent can English achievement in year 8 be explained by parents' socioeducational level, student sex, amount of homework, and attentiveness in class? English achievement is the dependent variable here. We have sex, socioeducation level of parents, amount of homework, and attentiveness in class. So it's just a standard multiple linear regression or simultaneous multiple linear regression. What I want you to do is do everything that we've just done in practice. So think about the level of measurement and get the descriptive statistics most appropriate for each variable. What's the sample size? Is it meet assumptions? Are our variables correlated? Are relationship linear? Run the regression, choose the same options as before for assumption checks, model fit, and standardized estimates. Evaluate the overall model. What's the strongest predictor using the standardized estimates and confidence intervals? Look for multivariate outliers with Cook's distance, normality of residuals using your QQ plot, and multicollinearity in addition to the fitted versus predicted values for your residuals. So go through each of those steps. I'll leave this up on the slide. I'm going to give you about 5 or 6 minutes to work through this, and then we'll regroup and have a chat about how you went. So try to work through the process of everything we did in that in the previous examples for regression. If you have any questions, let me know. Otherwise, we'll regroup in a few minutes. No worries, Emery. What sort of gibberish do you mean when you say it comes up as gibberish? What does it look like? This is what it should look like for you? What I'd recommend is probably just closing Jamovi, re-downloading the data file and opening Jamovi, see if that fixes it for you. No worries. Cool. How do we all go, guys? Are we hands up or put your hands up function if you managed to finish? Nice, thanks. Anyone else managed to get through the regression, running the regression model? No, I'll give you another 2 minutes and then we'll have a go together. That's really strange. Let me stop sharing and I'll download. Yeah, I'll give it a go as well. I'm finding it odd, the scrambling of the data. Let me look if it's something to do with the file. Because my this is the third tutorial today. No one's raised it, so let me have a look. Week 8, data file, dataset 2, download, open file. Yeah, I'm not sure what's going on. I'm not sure what the scrambling is. What you should do is take a screenshot and post it into the discussion forum, and I could have a look at it. But when I download it just then and open it up in Jamovi, it opens up fine. So I'm not sure what's going on there. Oh yeah, it's meant to say Engach. So that's English achievement. That's so ENGACH. That's just English achievement. Then you have can you hear me okay? Let me know. Okay, amazing. There was a momentary, I think it was like a power cut or something, but we're back. We're all the screens are back on. So let me just share video. Okay, excellent, excellent. So yeah, let me share my screen again. Sharing application screen, entire screen. So your data set should look like this. And so that's English achievement, sex, social education level, English homework, and attention. So how this should look in terms of the analyses is we're putting English achievement as I'll assume that you've done the correlation matrix and you've done your regression. So we'll run the linear regression, English achievement in the dependent variable, and the independent variables were sex, social education of parents, amount of homework, attentiveness in class. Pretty much everything else goes in here. And then for the assumption checks, We want collinearity, QQ plot, residual plot, Cook's distance, model fit, we want the F-test and adjusted R-squared. Model coefficients, we want the standardized estimates and confidence intervals, and that produces everything we've had in the previous examples. Looking at the QQ plot, we see pretty much a perfect QQ plot here. The middle of the distribution is very closely tied to the line, so that's excellent. In our residuals versus fitted, we have this diffuse cloud of dots, like a spread, like a scattergun of dots, no funneling or patterns. That's really good to see. And then those plots we don't need to worry about. Variance inflation factors less than 3, which is good, indicating no multicollinearity. Cook's distance less than 1, indicating no influential multivariate outlier. And then our model statistic is significant, indicating that it explains the variance better. It explains the model fits the data better than the mean of English achievement. Or accounted for by these 4 variables. Adjusted R-squared is a little lower because it's about the population level. Looking at our p-values in our different variables, we can see only English attention is significant and the rest are non-significant. So this says the more attention that's paid in English class, the higher the English achievement score. So specifically, every 1 unit increase in attention is associated with a 1.5% increase in English achievement. And then the standardized estimate is 0.375, so it's the largest effect. And this is statistically significant in terms of significantly bigger than socioeducation level, and no, that's the main one. It overlaps with the other two because 0.22 is less than 0.3 and less than 0.23. So it's only larger than socioeducation level. So those are the rundown of the key points when it comes to interpreting everything for that. This is again the questions to think about and how to do the write-up of what type of regression did you do, the assumptions. Were we okay on sample size linearity, multicollinearity, and distribution of residuals? Were there any multivariate outliers? And how well did our independent variables predict or explain our dependent variables? So this is what the write-up looks like. To assess the extent to which sex, parental, socioeducation status, English homework, and attentiveness in class predict English achievement, we first examined correlations between these variables. You did, we were a team, but I've put them here for you in this table. So here's what your correlation should have looked like. And so they suggest that students who pay more attention in class, do more homework, and were female achieve better outcomes in English, and confirm that associations were linear based on scatter plots and predictors were not overly correlated with each other. One thing we didn't do is interpret our sex effect here. So sex here, this is where you need to go to the variable and you need to see how is it coded. It says male is 0 and female is 1. So what that means here is this is referring to the difference between men and women, using men as the baseline because they're 0 and women are 1. So this is saying women on average have 0.616 higher English achievement than men, but it's non-significant. So really there's no difference between men and women there. Sample size was sufficient for simultaneous multiple linear regression, and our model indicated no issues with multivariate outliers. Cook's distance is less than 1, or maximum Cook's distance 0.05, with the residual plot suggesting a normal distribution. The overall model was significant and explained 21.9% of the variance in achievement, and here are those statistics just copied from that table. Attentiveness in class was the only significant predictor, exhibiting a moderate positive relationship with English achievement, such that those who were more attentive achieved better outcomes. If I was writing that really well, I'd say those that were more attentive achieved better outcomes after controlling for English homework, socioeducation level, and sex, because it's considering the covariates. The remaining predictor variables were not significant predictors, and therefore any apparent relationship with the DV could have come about by chance. And here's another example of how you can write that up. So this is a blend of the correlation table and the regression output. So you can actually put it all into one table, and you can just use the star system for indicating p-values, right? So you can see the p-values there. And there's the unstandardized beta estimates, standardized beta estimates, confidence intervals, and t-values. Excellent. So the fourth and final example is, can adding amount of homework and attentiveness in class explain additional variance over and above sex and socioeducation of the parents? So here is our model that we have now, but what I need you to do is actually create a hierarchical model. So we'll go into analyses, regression, linear regression, and we will put sex and English. Let me check which ones it were. Sex and socioeducation level of the parents. So we'll put sex and socioeducation level of the parents as covariates, English achievement as a dependent variable. And we could put the other two in as well, because we're going to use model builder. And so we want sex and socioeducation level of the parents as model 1, and model 2 to include English homework and attention. And then we want to select the usual statistics that we're needing here. Collinearity, QQ plot, residual plot, Cook's distance, F-test, adjusted R-squared, standardized estimate, confidence intervals. All right, so here is our first model and second model. Again, these show the difference between these models and the baseline, which is the mean of English achievement. Both are statistically significant, so both models explain the data better than the mean of English achievement, or fit the data better than the mean of English achievement. R-squared for the first model is 5%, second model is 21%, so the difference is 16%. And our adjusted R-squared for the population level is there, which are lower than the R-squared, but it's there. And then when we're looking at the estimates, well, Cook's distance is max is less than 1. Variance inflation factor is less than 3. QQ plot looks good. So all of these assumptions are very similar to what we had before, because the model 2 is essentially fitting the exact same. The only thing we're looking at differently is model 1. Why have I designed it this way? Because I want to show you something interesting that occurs. In model 1, when you look at the estimates, what do we see? Any thoughts or observations? What can you take away from this table here? The estimate for sex is quite high compared to education level of parents. So yes, so hopefully you're looking at the standardized estimate for that one, because that's the one you need for comparing size of effects between variables on different units. So yes, you see the size of the effect is larger for sex than standard socioeducation level of the parents, and this they do cross the intervals cross, so it's not significantly larger because 0.07 is within this range, but it is larger. What else do you notice here? Any other key observation? P-value becomes non-significant for SEL. Yeah, I think it was non-significant for both. So 0.446, model 2 is also 0.755. So SEL is non-significant both, but for sex it's non-significant in the second model, but in the first model it's less than 0.05. So here, this model says actually women, because remember women were 1 and men were 0, so this is comparing women to men. Women have 2% higher English achievement scores than men, and which is statistically significant in this model, after accounting for socioeducation level of parents. But when you account for socioeducation level of parents and English homework and attention in class, you can see that the difference in sex is no longer there. So this is largely accounted for attention in class, these other covariates that are there in the model. There's also another thing you can do in Jamovi, where if you have a factor, you can put it in here as a factor. It gives you the same result, but it actually tells you the levels of what they're comparing. So it says it's comparing women to men, and men are the baseline and women are the comparative group. But I still feel like I need to check the categorization to fully understand that. So that is the key difference between the two models. So this is why I talk about the importance of what these estimates mean in relation to the covariates. Each of these are saying this is the association between X and Y after adjusting for these covariates. Because we can see that in model 1, the effect of sex is significant, but in model 2, it's not significant. Another thing I want to draw your attention to is if we look at our data, you can see that there's lots of missingness here. Yeah. How R and Jamovi work is when you run a multiple linear regression model, if there is any data that has missingness in a cell, it actually does complete case removal. So this participant 2 and participant 1 are not included in this model. You see, because there's two, because we're using all of these variables, and so 2 of the variables. So you could say if we were to write a code in Jamovi to count up the missingness, this one has 2 missing cells. This one has 2 missing cells. This one has 1 missing cell, 1 missing cell, 1 missing cell. This one has 0 missing cells. This one has 2 missing cells, 0 missing cells, 0 missing cells, and you go on, right? So we could actually write a function that would do that for us rather than doing it manually. Why I've done that manually is just to showcase that in this model, only these 2 out of these 9 data points sample are included in the model. So when you look at the sample size here, it's 149, where our data, rather, have 242. So this is actually telling you we have removed the 90-odd data points from the analyses. So when we're looking at cases to variable ratio, you have to base it off this 149 figure, not this 242, because that's what's used for generating the model. Yeah, excellent. So how would our write-up change? Well, you say details of the assumptions are identical because the final model is the same, but the type of multiple linear regression is different. So this is hierarchical. And there are 2 models to describe predictors in the first step together, explain 5%, 5.7% of the variance in English achievement, and then these are the statistics, with sex the only significant predictor, indicating achievement was higher among females. The second step explained an additional 16.2% of the variance and revealed that with all predictors together, only attentiveness was significantly related to achievement, with more attentive students typically achieving better after controlling for socioeducation level of the parents, English homework, and sex. Yeah. So those are the key components of the write-up there. So those are all the examples. What I want to talk you through in the time we have left are some troubleshooting strategies. So what do you do if your sample size is not there? It's unlikely. There's a lot of, every student had to collect 5 data points, and there's, so I think there's over 500 data points there in the class data set. But what do you do if you have, say, a regression that has so many variables that you actually don't meet the sample size? So enough data is needed to provide reliable estimates of the correlations. If the sample size is small, we risk reporting findings that are unlikely to replicate if the study is repeated. As a general rule, you need 50 plus 8 times number of independent variables for reliably testing an overall regression model, and 104 plus whatever number of independent variables for reliably estimates for individual predictors. We did an example in the first case of this tutorial, showcasing what happens when you may not have a data set that has sufficient data, and in the write-up it accounts for that by just being transparent. Say that sample size is not enough, and so this can result in unreliable estimates either at the model level or the predictor level, depending on your sample size and which threshold you're able to meet. What if your assumptions aren't met for multivariate outliers? So Cook's distance analysis calculates a value for each participant. You can think of this as of how likely they are to be a multivariate outlier. The output will give the maximum Cook's distance value. So Cook's distance should not be greater than 1, which is hopefully drilled into your heads now. So there may be outliers if the maximum Cook's distance is above 1. As I said at the start of the tutorial, some programs such as R will show you the Cook's distance value for each participant, so you can find all the cases with the Cook's distance above 1 and investigate these, running the analyses with and without them to test whether they are influential outliers. You can't do this in Jamovi, and so you're not expected to do it in the lab report. For your lab report, all you need to do is comment on the likelihood of possible multivariate outliers. So it is either unlikely, so max Cook's distance below 1, or possible, which is when you have a Cook's distance above 1. So possible that there is at least one multivariate outlier. That's all you can say. I'm not expecting you to do anything more than that if you have a Cook's distance greater than 1. Just transparently say it. It'll be problematic if your Cook's distance is greater than 1 and you don't address it by transparently stating that it's possible there's at least one multivariate outlier. So just be transparent in your results. What if your assumptions are not met for multicollinearity? Well, that's a potential problem if we've looked at all these avenues. Correlation matrix show large correlations greater than 0.7 among any predictor variables. Tolerance values are less than 0.3, or variance inflation factor is greater than 3. You only need to check one of these. If this is the case for your lab report, you could always just reconsider the choice of your predictor variables if multicollinearity is present. So consider whether you should choose a different independent variable so that you don't have multicollinearity present. So that's one option available to you. What about normality of residuals? Recall that residuals are the difference between predicted and observed scores, and these can be positive or negative. On average, the residual should equal 0 and be normally distributed. So again, this diagram here is to show, again, from the lectures, how you have data points, you have your line of best fit, and this is the predicted values. And so the residuals are the difference between your data points and the predicted values. And on average, you want them to, the average residuals to equal 0. Error is random, therefore residuals should be normally distributed around 0. What happens if it's not? Well, remember that minor deviations are okay. It's unlikely that your QQ plot or residual versus fitted plot will look perfect. And again, we're only concerned if they show clear deviations from normality. We looked at a various number of plots today, some that were perfect and others that were less perfect, but they were all acceptable. So it shows you sort of a range of values. What if your residuals are not normally distributed? Try and reflect on why this might be the case. Most often than not, this is most likely cause of non-normal distribution of residuals is non-normal variables. So often at times, if you look at your variables, you see one is very skewed, and you see you have non-normal residuals. It's likely that skewed variable that's influencing the residuals. What you need to do is just include a statement indicating that the distribution of residuals is non-normal and what this means. As violations of this assumption reduce the p-value, so you might be more likely to make type 1 errors. So really, yeah, don't panic. You're not going to fail if the assumption is violated, but you do lose marks if you ignore it. If your residuals are non-normally distributed, you just ignore it, you'll lose marks. If you state that they're non-normal and this has the possibility, and this is where you reduce this risk of error by focusing on effect sizes and include confidence intervals rather than focusing solely on p-values, which should be the case regardless of whether or not your residuals are normally or non-normally distributed, but it's even more important when they are non-normally distributed. So these are the types of strategies you can use for your lab report should you encounter these challenges. Again, as a reminder from the lecture, here's what we're looking for in that residual versus predicted value plot. This diffuse cloud of dots is normal. Here is a heteroscedastic plot rather, this clear funneling that's occurring. Over here we have nonlinearity that's occurring, and here we have heteroscedasticity and nonlinearity, right? So you have both that's occurring. So really you want your data to be looking like the top left when you plot it. So when you do your analyses of residuals, this can pick up an outlier you may have missed in data screening, which is an easy fix. If this is the case, report the results after dealing with the out of range data. You can see if the results change when you include or exclude your outliers using filters in Jamovi that we've done in previous tutorials. Analyses of residuals can highlight restriction of range on your variables. In this case, you should comment that the residual plot shows some evidence of restriction of range. Investigate which variable or variables in your regression might have restricted range. But really, you should already know this if it was a problem from looking at your univariate statistics. You can see if any of the variables have this restricted of range, and if not, check histograms of the constructs that went into your multiple linear regression. You can still report your multiple linear regression results providing data are still normally distributed, but this would just be a limitation of your research. So analysis of residuals can pick up also not only on outliers and restriction of range, but skewed data. Recall that an assumption of multiple linear regression analysis is that continuous data is normally distributed. So severe skew or kurtosis violates this. If this is in one of your predictor variables and you still want to use it in analysis, just consider recoding it down to a categorical or dichotomous variable. So, in saying that, that's it for today. If you have any further questions, feel free to ask them on discussion forums in the threads. But that's it for today. So you've mastered the art of multiple linear regression, just as I'm losing my voice. Sorry. So if you have questions, let me know. Otherwise, go forth with your understanding of multiple linear regression analyses and take that forward with your lab report. Have a lovely day, lovely week. I'll see you guys in the next tutorial. Yeah. No worries. See you guys.